Welcome to the Symmetric Key. In response to Cryptanalysis lecture, we'll be learning more about symmetric key encryption. In lesson 2 of this module, we briefly looked at a history of cryptography. Now that we have learned about transposition and substitution ciphers and monoalphabetic and polyalphabetic ciphers, let's look at the historical timelines of cryptography again as we head into this lesson about symmetric key cryptography. I like that the first one shows when certain methods were broken. And I like that the second one goes to near present day and includes specific algorithms. Let's take a look at that a little bit before we move on. We also have a 3-part series on crypto across time, the past, present, and future that could be helpful. There's a link on the last slide. Classical and modern ciphers differ significantly in their design, strength, and application. So let's look at these differences to help us understand the inception of modern cryptography. So if we look at the aspect of security and algorithms, classical ciphers rely on obscurity and simple transformations. Caesar cipher. Modern ciphers, however, use complex mathematical structures, modular arithmetic, confusion, diffusion. When speaking about computational requirements, classical ciphers can be computed manually, pencil and paper, where modern ciphers require computational resources for encryption and decryption. With key space and resistance to cryptanalysis, the classic ciphers have small key spaces. They're vulnerable to brute force, and they're vulnerable to frequency analysis. Where modern ciphers use large key spaces like the AES 256, which are resistant to brute force, frequency analysis, and cryptanalysis techniques, like differential and linear. This is a good time to introduce Kirchhoff's principle, one of the basic principles of modern cryptography. Kirchhoff's principle states that a cryptographic system's security should depend on the secrecy of its key and not the secrecy of its algorithm. The principle is widely accepted by cryptographers. It is in contrast to the security through obscurity, which is not accepted. Relating this to what we just talked about, on the basis of security and algorithms, Kirchhoff's principles state that classical ciphers violate Kirchhoff's principle by relying on algorithm secrecy. Modern ciphers follow the principle where the algorithm is public, but the key is kept secret. In regards to key space and cryptanalysis, modern ciphers adhere to Kirchhoff's principle by designing large key spaces. Speak about that in a little bit. This makes the secrecy of the key more important than the algorithm itself. In essence, classical ciphers don't align with Kirchhoff's principle because their security depends on keeping the algorithm secret, while modern ciphers embrace the principle by relying on the secrecy of the key, assuming the algorithm itself is public. So recognizing the weaknesses of classical methods, cryptographers moved to mathematically secure encryption with significantly longer key spaces. In this lesson, we learn about symmetric key cryptography. In the next lesson, we will learn about asymmetric key cryptography. So symmetric key cryptography, is like using the same key to lock and unlock a door. In simple terms, we have one key for both encryption and decryption. The same secret key is used to scramble, encrypt, and unscramble, decrypt the data. Both sender and receiver must have the same key, so they need a safe way to exchange it. Also, at the end of the lecture, the last slide includes a 5-minute video regarding symmetric key encryption that you might want to watch. So, hey, this sort of sounds like the same as classical methods, right? That we talked about last lesson. The differences are key length, space out, just space, algorithm complexity, and key management. We'll talk about a couple of those here. So key length, in symmetric key cryptography, the key length, which is measured in bits, determines the size of the key space, which is the total number of possible keys. Key length refers to the size of the key, the secret number or string, used in the encryption process. It's typically measured in bits. Longer keys equal stronger security. The longer the key, the harder it is for an attacker to guess or break it by trying every possible combination, right? A brute force attack. Key length is how long the secret key is. Key space is how many possible keys there are for a given key length. For example, we have a 56-bit DES, which is a key length of 2 to the power of 56. That was broken in 1999. 128-bit AES has a length of 2 to the power of 128. So even that is not practically breakable today. And we have a 256-bit AES, which is 2 to the power of 256 long, and that is considered quantum resistant. So if we look at this, some common symmetric key lengths and their security, you can see them on the slide. There's a couple other ones that we could mention. There's a triple DES, 3DES, which is 112-bit. It's deprecated. It is weak against some attacks. There's a blowfish algorithm that is between 32 and 448 bits. It's secure, but it's slower than AES. And there's the Cha-Cha 20. It's a 256-bit. It is secure, and it is a fast alternative to AES. Increasing the key length improves security in the following ways. One, it increases the possibility for more possible keys. A longer key means a larger key space, making brute force attacks infeasible. 2, some cryptographic algorithms utilize prime numbers in key generation to ensure high entropy and unpredictability. It protects against Moore's law. As computing power increases, longer keys ensure encryption remains secure. And also increasing the key length improves the resistance to quantum computing. As mentioned earlier, AES 256 is considered resistant to Grover's algorithm, which could weaken symmetric encryption. While key lengths deal with how many possible keys there are, right? That's the size of the key space. Algorithm complexity refers to the design and strength of the encryption process itself. A complex algorithm ensures that even if you have a lot of computational power and a potentially long key, breaking the encryption remains difficult due to the way the data are processed. We're not going to go deep here, but here's a few ways that symmetric key algorithm can add complexity. Many symmetric encryption algorithms use a combination of substitution and permutation in multiple rounds. This structure is referred to as an SP, or substitution permutation network. For example, DES, which is the data encryption standard, uses a combination of substitution, using S boxes, and permutation, P boxes, to obscure the plain text. Even if part of the data is known, the use of multiple rounds and transformations makes it hard to reverse the process. More specifically, in DES, the data is divided into smaller blocks and passed through a series of transformations. Substitution, with each 6-bit input is replaced with a 4-bit output using substitution boxes, those are the S boxes, and also works with permutation. The data is rearranged in each round through a permutation box or a P box to further increase confusion. Some symmetric algorithms use key expansion, where the original key is used to generate multiple keys for each round of encryption. This increases the computational complexity and further diffuses the key across multiple stages of the encryption process. For example, AES uses key expansion to derive a set of keys from the original key, which are then used in the rounds. AES with 128-bit key length performs 10 rounds. AES 192 performs 12 rounds, and AES 256 performs 14 rounds. Each round involves a series of operations, substitution, permutation, mixing, and adding keys, making it increasingly difficult to reverse the process without the correct key. So more specifically, with round key generation, the key is expanded into larger sets of keys, or larger set of keys, each used in different rounds. The rounds, or each round modifies the data through substitution, mixing, and adding round keys, all of which increase the algorithm's resistance to attacks. We don't expect you to understand the technical details of algorithm complexity, but we do want you to understand and appreciate that modern cryptography uses advanced methods, some based on the past, to create complex algorithms. And we want you to remember the key length determines how many keys there are to guess, right? A larger key length increases security against brute force attacks. Whereas algorithm complexity determines how much harder it is to break the encryption using cryptanalytic analytics, again, easy for me to say, methods regardless of key length. So now let's look, so when you're finished with this lecture, you're going to look at key management. So some of the strengths of symmetric key cryptography, again, we kind of talked about them. I want to repeat them. The speed of symmetric key cryptography. It's generally faster than asymmetric cryptography, which is covered in the next lesson. Efficiency, it requires less computational resources, and there is strong security when implemented properly with sufficient key length. However, there are some limitations of symmetric key cryptography. One, the key distribution problem. How do we share this key securely? Key management. Okay, there's difficulty managing many keys for multiple parties, and you'll get that in the next part of this lesson. And there are some scalability issues. So again, next up in this lesson, you'll learn why key management is the Achilles heel of symmetric key cryptography. So we do want you to consider some questions here after this. One, how does Kirchhoff's principle influence modern cryptographic design? Two, what real-world applications rely heavily on symmetric encryption? And three, how might quantum computing affect symmetric key algorithms? Oops, we lost that. Bring it back here. So the last slide then has the links for some additional resources, and I hope you enjoy them. Thanks.